Hello, I'm Charlie Thompson, and this is the intro video for Lab 5 on pressure and wind. So we're playing with driving forces in the atmosphere. There's 4 reasons that we have wind. So really quickly, I'm going to go through what the 4 basic reasons are that we have wind. I don't mean for this to be a substitute for your regular lecture class. Like all the details about why we have wind and the 4 forces, that should be covered in your lecture class. But really quickly, just as a reminder, there's 4 forces that give us wind. So there's gravity, there's the pressure gradient force, Coriolis force, and then finally friction force. And the 4 of these forces together combine to create wind patterns at the surface. So first off, gravitational force. I think that's the cheesiest of all of them. No gravity, no atmosphere. Gravity is just pulling everything to the center of the Earth. So without gravity, we wouldn't have any atmosphere. The pressure gradient force is the most important force in driving wind. Pressure gradient force is the idea that air flows from high air pressure to low air pressure. If you let air out of a balloon, out of a tire, air flows from high pressure to low air pressure. If there's no difference in air pressure between 2 places, there's no wind. So the bigger the difference in air pressure between 2 places, the stronger the pressure gradient force is going to be, and the higher the wind speed is going to be as a result. So pressure gradient force is easily the most important force that drives wind. In fact, without pressure gradient force, it doesn't matter that we have gravity because there won't be any wind. And the other 2 forces, Coriolis and friction, only act on air that's moving. So if the air isn't moving, there's no Coriolis deflection, there's no friction. So pressure gradient force is really, that's the force that begins air moving and keeps it moving. So on maps of air pressure, so these are isobars. Isobars are lines of equal air pressure. Where the lines are really close together, that's where we find the strongest wind speed, and where the lines are farther apart, that's where we have lighter or weaker winds, because there's less of a difference in pressure. Here, there's an enormous difference in pressure between, let's just say, here and here, and here. Between these 2 lines, well, between each line, between each set of lines on a standard air pressure map, there's 4 millibars of difference. Remember, standard air pressure is 1013.2 millibars. So there's 4 millibars from here to here. And from here to here, there's 20 millibars. So you'd expect the wind to be much, much stronger where there's 20 millibars of change over that, rather than only 4 millibars of change. Steep pressure gradient, the lines are close together, high winds. On a topographic map, if the lines are close together, that means that there's a cliff. There's very rapid elevation change. Shallow pressure gradient, the lines are far apart, and you have low wind speed. So this is an upper air plot of wind speed at the 500 millibar level. You can see the lines are really far apart here. In fact, there's nothing, like there's one line here, and then there's another line up here. And indeed, in this area, the wind speeds are 5 knots, 10 knots, 20 knots, 10 knots, 20 knots, 10 knots, 5 knots, 5 knots, 5 knots. So even though we're halfway up through the atmosphere, the wind speed is really low. Over here, you can see that the lines are much closer together, so that's a really steep pressure gradient. And indeed, in this section, the wind speed right here, showing the direction of wind, 5 knots down there, up there, 90 knots. So when the lines are close together, the wind speed is much, much, much stronger. Coriolis force is the most difficult to explain, and really, if you can remember that moving objects are deflected to their right in the northern hemisphere, you're golden. Moving objects, as they move along, get deflected to their right in the northern hemisphere. I'll put up some videos on Coriolis force. If you come across a good video on Coriolis force that really does a great job of explaining it, please send it my way. I haven't seen one yet. Moving objects are deflected to their left in the southern hemisphere. So Coriolis force is caused by the different speed and rotation of Earth. At the equator, Earth is spinning about 1,000 miles an hour, and at the poles, it's spinning 0 miles an hour. So everything that travels from the equator to the poles is moving sideways and keeps that sideways momentum. So as they move north, they're deflected to their right. As objects move south from the equator, they're deflected to their left. So friction, the last force, only acts on moving air. Friction slows down wind speed, and it reduces the Coriolis force from the surface up to about 500 meters, which is about 1,500 feet. So once you're above 1,500 feet off the ground, there isn't the friction effect of wind against the ground. So the wind speeds are higher. Like if you've ever flown a kite, you know this. If you can get a kite off the ground, you can usually keep it up because once you're off the ground, there isn't that friction effect, and so the wind speed is stronger. And it also, that friction also reduces Coriolis force. We'll take a look at that in just a minute. At the surface, air flows out at a 45-degree angle to the pressure gradient force. But once you're above 1,500 meters, or 1,500 feet rather, 500 meters, 1,500 feet, the two forces acting on wind are pressure gradient and Coriolis, so the air flows perpendicular to the pressure gradient force. Above 500 meters, no friction. The winds there we call geostrophic. In fact, if I just back this up for a sec. Right. Get rid of all that. These are geostrophic winds. Here is higher air pressure. Here is lower air pressure. You can see that the air is rotating counterclockwise around this area of low pressure. This is probably an area of high pressure, so it's rotating clockwise. But the air, as it flowed from high pressure to low pressure, started to flow from high to low, got deflected by Coriolis, and then it just flows at a right angle to the pressure gradient. So if this was high, it is high pressure to low pressure. Because of the pressure gradient force, it's flowing to low pressure, but then Coriolis in the northern hemisphere deflects it to the right, and it just keeps going to the right. So put all this together, and if there's high pressure, it means that there's air that is sinking and spreading out when it hits the ground. That's called an anticyclone. If there's low pressure, the air is coming together and rising. So low pressure is associated with clouds, high pressure, sunny skies. Low pressure, the air comes together and rises. Let's take a look. So in the northern hemisphere, air flows into low pressure, rotating counterclockwise. In the southern hemisphere, air flows into low pressure, rotating clockwise. In the northern hemisphere, if there's high pressure, the air is sinking and then spreading out, rotating clockwise. The air is moving out, deflected to its right, moving out, deflected to its right, making a clockwise pattern of rotation around high pressure. And then low pressure, the air flows in and rotates counterclockwise in the northern hemisphere because of Coriolis deflection. As the air flows in, it rotates counterclockwise into low pressure. In the southern hemisphere, those directions are reversed. If there's high pressure, it rotates counterclockwise. Low pressure rotates clockwise. I'll just say that in the northern hemisphere, surface winds spiral clockwise out of the high pressure. In the northern hemisphere, winds spiral counterclockwise into low pressure. So here's a quick animation showing rising air. If there's low pressure, the air converges, comes together, and rises. As the air rises, it expands, it cools, you get clouds. If there's high pressure, it means that the air is sinking. As it sinks, it gets compressed, and then it spreads out, flowing clockwise in the northern hemisphere. So I'm going to put this together in a static, unmoving, animated kind of way, just to go through those four forces. Well, we could ignore gravity. So right now I've got pressure gradient in red. This is the northern hemisphere. Here's high pressure. There's low pressure all around, but I didn't want to take the time to make a dozen little areas of low pressure and all the arrows. So air flows from high pressure to low pressure. Coriolis force in blue deflects it to the right. Friction slightly counteracts it. So in the northern hemisphere, wind, shown by the black arrows, is going to rotate out clockwise. In the northern hemisphere, if there's low pressure, The air is flowing from high pressure to low pressure. Coriolis diverts it to the right. Friction slightly reduces the Coriolis. So the pattern of wind flowing into an area of low pressure, the air is going to be flowing in and rotating counterclockwise. Okay, so looking at upper airflow or geostrophic flow, we have an area of high pressure in the upper atmosphere. So the pressure gradient force, air is spreading out from the high. So you have to imagine there's high pressure here and then low pressure all around. So the air starts to flow out from the high pressure. It gets deflected to its right by Coriolis. So then the wind is just going to blow perpendicular to the pressure gradient force. This is what I meant before when I said the air starts to flow based on the pressure gradient force, gets deflected by Coriolis, and so it just keeps going around and around and around in a circle. So in the northern hemisphere, high pressure flows clockwise. If we had low pressure in the upper atmosphere, the air would start to flow in from high pressure to low pressure. It's going to get deflected by Coriolis. And then the pattern of wind, it's going to flow counterclockwise around an area of low pressure. Again, perpendicular to the pressure gradient force, parallel to the isobars, as opposed to surface winds, which are going to flow at a 45. So here we've got global patterns of air pressure. This is an idealized situation of air pressure. This is January. So we have low pressure along the equator with the ITCZ, the Intertropical Convergence Zone. That's going to shift north and south with the subsolar point over the year. It's going to cause the Asian monsoon. This is the winter pattern. So in winter, we've got the ITCZ. It's shifted south with the subsolar point. We have the subtropical high pressure cells, the Azores and Hawaiian highs. We have the Aleutian low along the polar front, the Icelandic low along the polar front, and then we've got the Central Asian high pressure area. So there's high pressure here, low pressure here. So in India, in the wintertime, there's high pressure inland, low pressure offshore. So the wind blows offshore. And as the wind blows offshore, it goes over these mountains, the Tibetan Plateau, about 15,000 feet. And then the air sinks down to sea level. And as it sinks, it gets compressed, it gets heated up. And so in the winter in India, it's dry. The wind is blowing offshore, and it's hot, and it's dry, and it's dusty in the winter. In the winter in California, the Hawaiian high shifts south, the Aleutian low strengthens, and so storms track parallel to these isobars, and we get rain in the winter because the Hawaiian high shifts out of the way. In years when it's a drought in California, the Hawaiian high doesn't shift. It just stays there and it blocks the storms. And so Canada, Vancouver, Seattle, they're going to get lots and lots of rain because we're not, because our storms are going to get deflected up. So that's January. In July, the ITCZ shifts north. You can see the Pacific high gets gnarly strong, which is going to deflect storms up into Canada now. The Bermuda high doing the same thing over in Europe. But over in Asia, the ITCZ has shifted well inland. So now there's high pressure offshore, low pressure inland. So this is the rainy season. You've got wind blowing across the ocean, hitting India, the land, and then getting lift up. As the air is lifted up, it expands and it cools, and you get lots of rain. This also sets up the pattern of global wind belts. So flowing out of the subtropical highs are two of the most important wind belts on Earth. There's the trade winds. These are the northeast trades flowing out of the high to the equator, flowing out of the high to the equator, flowing out of the high to the equator. And then these are the southeast trade winds flowing out of the subtropical high, flowing out clockwise, flowing out clockwise, flowing out counterclockwise. High pressure in the southern hemisphere flows out counterclockwise. In the northern hemisphere, it flows clockwise. So these are the northeast trades. These are the southeast trades. Those two wind belts make up the trade winds. And then there's the westerlies flowing out of the subtropical high to the polar front are the westerlies. They're called westerlies because the wind comes from the west and goes to the east. Those are the prevailing winds in the mid-latitudes, are the westerlies. And then in July, everything shifts north with the sun. So now we've got onshore winds bringing hot or warm, moist air into India, where it produces lots of rain. The Pacific high is going to block our storms. As they come across, they're going to get deflected and end up in Canada. So those are the main pressure belts, the ITCZ, the Intertropical Convergence Zone, an area of low pressure where air is coming from the subtropics to the equator, rising and then sinking, making the subtropical highs, the Pacific high, the Bermuda high, also called the Hawaiian high, also called the Azores high. And then those subtropical high pressure cells in the ITCZ make the trade winds. And then going from the subtropical high pressure cells to the polar front, that's going to set up the westerlies. So for the practical part of the lab, I thought about doing paper exercises or math or something. Anyway, I gave up and thought, what I really want them to know is patterns of high pressure, low pressure, and where those areas of high pressure and low pressure are. And so you could look at what the diagrams in the book show and then compare them to reality, because the diagrams in the book are often long-term averages, but everything's constantly changing. Earth is very complex. So I thought, you know what I do when I want to know what the wind, what the weather, what the air pressure, I go to a website. So this is earth.nullschool.net. This is a screenshot from the website. And this is the way it's going to look. I'm going to give you a URL, a web link, and you'll click on it. It'll open up the web page. And then I'll ask you, hey, in this bounding box, in this region, tell me about the wind and air pressure. So this is with everything turned off. This is with everything turned off so that you could see the grid. And there's a 10-degree latitude longitude grid under everything. If you pause the animations, it might make it easier to see if you get confused. But if you want to know where you are, where you're looking at, you just need to click. When you click, you'll get a little green circle. And in the lower, when you click, you'll get a little green circle. And then in the lower left, it'll pop up and it'll tell you the latitude, 40 degrees north, the longitude, 140 degrees west, and information about the theme you had loaded. So I had wind and pressure, and it's telling me what the wind speed and direction are. 23 knots coming from 195 degrees. And the air pressure is 1,029 hectopascals. So hectopascals are the same as millibars. So it's going to give you numbers in hectopascals. Those are the same as millibars. Just there's no conversion. 1 millibar is 1 hectopascal. So like I said, you click and it's going to show you this is 40 degrees north, 140 west. So this would be 50 degrees north, 140 west, 50 degrees north, 150 degrees west, 50 degrees north, 160, 170, 180, there's the international date line, and then it goes 170 east, 160, 150, 140, 130. But like I said, you can click any place on the map and it'll tell you what the latitude, longitude, and other information is. Some other things about the map before we get started. Down in the bottom, if you click on the word Earth, it reveals other information. For example, the legend. And if this was live and not a screenshot, when you mouse over it, it'll tell you, like that particular color, what the air pressure is. That color, what the air pressure is. You can turn on and off the animation. You can go back a day. You can go back 3 hours, forward 3 hours, forward a day. Pick a date. Turn on more lat-long grid. Change what you're looking at. Are you looking at the atmosphere, the ocean, chemicals in the atmosphere, particulate matter? Are you looking at the surface, at the 1,850 millibar, 700 millibar, 500 millibar, 250? Are you looking at wind speed, temperatures, relative humidity, a bunch of other factors? When it opens up, it'll be just like this. In fact, it'll be exactly like this because that's the link that I sent you. So I thought about what the best way to ask you questions, because again, I don't want you to have to feel like you're going to have to click on the whole map to give me an answer. So I thought, I'll use the idea of bounding boxes. So I'm going to give you a diagram and what the latitude and longitude values are with that box. So this is going from 30 degrees north to 40 degrees north, and then from 130 west to 140 west. So it's this box in this particular question would be 10 degrees high by 10 degrees wide. And then on the map, this is where that box would be. So this is 40 degrees north, 30 degrees north. This is 140 degrees west. This is 130 degrees west. 140 west, 130 west, 40 north, 30 north. So that would be the bounding box. Oh, there won't be, I put in this big green box as an example. The green boxes don't show up on the map. You'll just have nothing. If you click, you can get the green circle. I added in the green boxes to show you the correlation that when I'm talking about this area, 140 west to 130 west, 40 north to 30 north, I mean this exact area. And the way you'd know that is if you click right there, it'd say that's 40 degrees north. If you click here, it would say that's 30 degrees north. If you click here, it would say 140 degrees west. If you click here, it would say 130 degrees west. So to make sure, you could just start with whatever the highest latitude, longitude values are, and then the lowest. So the highest is 40 degrees north, the lowest is 30 degrees north, the highest longitude is 140, and the lowest is 130. So this would be 40, 140, this would be 30, 130. And then you would click in the box and try to find the highest air pressure, the lowest air pressure, whatever the question's asking you. So another example, so this one now is 10 degrees high by 20 degrees wide. So this is actually going to be two boxes. So it's going from 150 to 160, 160 to 170, 60 degrees north to 50 degrees north. So now we're at 170, 160, 150. Remember that was 40 degrees, that's 50 degrees, so that's 60. So there's 60 north, there's 50 north, 170 west, 150 west. And then finally, this is another two-box combo. Oh no, I'm sorry. I got excited. It's 4, right? Because 90 to 100, 100 to 110, 30 to 40, 40 to 50. So this on the screen should be, 4 boxes, right? So those numbers again, 30 north to 50 north. So if that's 40, that's 30, 40, 50. And if that was 140, 130, 120, 110 west, and 90 west. So the lowest values would be 30 north, 90 west, and the highest values would be 50 north, 110 west. 50 north, 110 west, and then 30 north, 90 west. And then answer questions about the space inside that box. And just I'll say it again to keep you from being disappointed. The green box is a green box that I have added. On the test questions, it'll just be, hey, here's the box, here's the link, you go figure it out, let me know. All right, that's it for this part of pressure and wind. Let me get out of this. Let me go over here. So this is with everything turned off. And this is the way the page will look. And I'm sorry, I lied. This is the way it's going to look. So let's start that all again. Okay, when you click on the link in the question, you should see a page that looks like this. If you don't, something's gone wrong. So again, it's the same area that we were looking at in screenshots. You can see there's air swirling out of the high pressure areas, swirling into. If it's moving into an area, that's low pressure. If it's blowing out of an area, it's blowing out of high pressure. And then again, you can click on a region. Like if I wanted to know the lat long for the tip of Florida, looks like it's 25 degrees north, 80 degrees west. And then here's, again, 40 degrees north, 140 west, 40, 130, 40 north, 120, 60 degrees north, 170 west. This should be 60 degrees north, 150 west. You can also zoom in. I guess that's zooming out. And then I'll reload. You can zoom in. You can click and drag if you want to move something to the center of the screen. And then you can just kind of push things back the way they were. You can click and drag, zoom out, get the whole picture. That should do it. As soon as I stop moving, it'll turn back on. Boom, there you go. Oh. And there you go again. So we'll be using this again in the next lab. The next lab's going to be about weather. So some of the things we could do, we'll turn on the amount of water vapor in the atmosphere, which is now showing orange is dry, light blue is really wet. And you can see the ITCZ. Oh, that's amazing. We can turn on clouds, and you can see the ITCZ again, that belt of clouds. And then here along the polar front, the warm air is coming up, the cold air is coming down, they collide. That's where you get storms. If I go back to wind, now it'll be color-coded by wind speed. And finally, if I take us to today, you can see some really interesting things going on. Especially, boom, there you go, little? Are you a hurricane yet? 67, almost hurricane strength. To be a hurricane, you have to be 75 miles an hour. So we're almost there. Also another little tropical storm. We'll play with this later. That's it for this lab. I wish you good luck on Lab 5, Pressure and Winds.